Our next unit in the topic of waves is sound. So the learning objectives are highlighted there. By the end of the unit, you should be able to do the following learning objectives. Okay, the black ones are for those who are doing double point, and the red ones are for those who are doing triple point. So sound. Sound is produced by vibrating objects. And the sound wave consists of a mechanical vibration in air and other substances. So because it's a mechanical vibration, it's going to need a medium like air. And sound is, from our previous lessons, a longitudinal wave in which the wave energy travels, of course, in the same direction as the particles within the wave. Okay, that's what it means to be longitudinal. That's the definition. So remembering the wave direction and the vibrations are in the same direction, that way it is a longitudinal. So here are some air particles just floating about doing their thing, and there's no sound wave. And then what happens is that we have someone talking, like one of you from the back row, and you see that the sound waves interact with the air molecules. With the air molecules get compressed. Okay, this is where this part here is, and where they get spread out, which is the area here, which we call a rarefaction. So a compression is a region of slightly higher pressure where the air molecules are closer together than usual, and the rarefaction is the opposite of that, where they're more spread out. And a wavelength is going to be the distance between the maximas of the compressions, or alternatively the minima of the rarefactions. So the human range of hearing. Humans can hear sound frequencies within the range of 20 Hz and 20,000 Hz. As I'm getting older, I have a shorter range of only 20 Hz to about 17,000 Hz, but you young students should have that range. Okay, as age and damage reduces the upper limit. So an old person like myself, okay, not that old, but someone exposed to prolonged high sound volume, say working at an airport, that's why they have those headphones on, may no longer eventually hear above 10,000 Hz. Okay, so when you're about 70 or 80. And some animals, of course, can hear higher frequencies. For example, bats and dolphins can hear up to 100,000 Hz. And dogs between 40 and 60,000 Hz. That's how a dog whistle works, okay? You blow a dog whistle, you can't hear anything because your upper range is 20,000 Hz, but it makes the dogs go crazy because their upper range is between 40 and 60,000 Hz, which they can hear, but you can't. Okay, so now looking at ultrasound and infrasound. So ultrasound is the higher frequencies above 20,000, so dogs can hear it, but we can't because it's too high for our upper limit. And ultrasound can be used to measure distance. Okay, so in this GIF here, we're looking at something called sonar, or for medical applications like scans. So ultrasound is something that, say, a pregnant woman would take an ultrasound to see how the baby's going, because it can see inside objects, the human uterus, as an example. Okay, and infrasound is a low frequency sound, inaudible to humans, although we may feel it as very slow vibrations. And earthquakes, waves, an example of infrasound. So elephants are thought to be able to actually hear this infrasound and are aware that an earthquake is actually coming and are able to escape. So sound waves, of course, need a medium because they're mechanical waves and they can move through different materials. And sound travels quickest through the solids because the particles are all nice and close together, so the energy can transfer quickly. So a train can often be heard, a bit of a spelling mistake there, approaching through the rails before it can be heard through the air. Okay, so if you've ever seen the cowboy and western movies, when the bank robbers want to rob a train, they always put their ear towards the rails to see the train that's coming or not, and give them some time to prepare their ambush. And sound travels well also through liquids. For example, whales can communicate great distances underwater because of this. And sadly, sound travels slowest through the gases, like our atmosphere. And the speed of sound increases with temperature. And why does sound not travel through a vacuum? Well, the reason being, of course, sound doesn't travel through space because there's no medium for that energy to transfer. Okay, so in a gas, there's the medium of the gas particles. In a solid, the same, you've got the medium of the solid. But, of course, in space, no one can hear you scream. Okay, so this is an experiment that we're going to demonstrate in class, known as the bell jar experiment, which illustrates that indeed sound is a longitudinal wave that requires a medium in order to operate. So what happens is you've got a jar basically containing a bell. The air is removed from the jar using a vacuum pump, so it leaves a vacuum in the jar, and you basically turn the bell on, and theoretically, well, not theoretically, you should not be able to hear the bell because you need that medium of the air inside the chamber of the bell jar in order for the sound to move. Okay, so this is basically proving that you need a medium for the transmission or the passing of the sound waves. So as the air pressure inside the bell jar is removed, okay, or reduced to a vacuum, the loudness of the sound should be heard to decrease, and the bell can be seen, or it's a glass jar, to be banging, but it cannot be heard because there is no medium now for the sound to be transmitted. Okay, and we'll now look at the reflection of sound. So an echo is a reflected sound wave. Okay, so here's a short question for you. A misguided student shouts Chelsea for the FA Cup at a nearby cliff and hears an echo 1.4 seconds later. How far away is the cliff, given that the speed of sound is 340 meters per second? Okay, so pause the video now and see if you can come up with an answer. Right, so maybe a diagram could help. So here is this foolish child who thinks Chelsea's going to win the FA Cup near the cliff here at a certain distance d. Okay. So the sound travels to and from the cliff a total distance of 2d. So speed equals distance over time. So you can rearrange the equation to give distance equals speed times time. So 340 times 1.4, which will give 476 meters. However, that is twice the distance that the sound has traveled. So you divide that by 2, so it's going to be 238 meters. Okay, so just like light, sound can be bent or refracted. So here is me yelling at a couple of students. Okay, one student, C, is right next to me next to the side of a lake. The other student's on the other side of the lake, student B. Okay, and because the air over the lake is a lot cooler, it's a lot denser. Okay, so the sound produced by person A will be heard more clearly by person B than by person C. And the reason why, of course, is the cooler air over the water refracts the sound downwards, okay, towards the normal, as it were, because the cooler air is actually denser than the hotter air near the lake. Okay, so now looking at the triple only, okay, sound diffraction. So a typical sound wave has a wavelength of about a meter, about the same as the open wave, the width of a doorway. Okay, therefore sound undergoes significant diffraction at a doorway or around the corner of a building. This is why you can hear, hopefully, somebody in such circumstances even though we can't see them. It appears that the sound may have bent, but it's actually just diffraction. Okay, so we've got some juicy gossip happening in ME8. Okay, the doors are wide open. It's kind of reflected off the door and actually refracted around so I can hear it in ME9 with my door open. Okay, so why does light not diffract as much as sound? So if you could pause the video now and maybe think about that. Okay, so the reason why light does not diffract as much as sound is because the wavelength of light is a lot smaller. Okay, a lot smaller than the door aperture. Okay, remembering the size of the aperture depending to the wavelength is very much how much or the size of the diffraction. Okay, so measuring the speed of sound, which is usually a common experiment question used in exams. Okay, the first thing you have to do is use a visible loud event. Okay, so maybe me firing off a shotgun. Okay, so, or a cannon, even in this image here. Use a stopwatch to time the difference between seeing and hearing the event. So you see a cannon explode, and then you can hear the cannon fire. You then measure the distance between the event and where you are, and speed equals distance times divided by time. But remember, the distance should be as large as possible in order to avoid the significant reaction time error in timing the measurement. The larger the distance, the less error in the timing. Question. So, a group of students measure the time it taken between seeing and hearing another student 250 meters away, clashing two pieces of wood together. They obtain the following timings. Use their measurements to obtain the speed of sound estimate. Okay, so pause the video now and see if you can work out their actual speed of sound estimate. Okay, so welcome back. So the first thing you have to do, of course, is take the average to reduce the random error. So you should get an average time of around about 0.756 seconds. Okay, and then speed will equal distance over time. 250 over 0.756 seconds is going to be 4.08 kilometers, or 4,080 meters. Okay, so the speed of sound should be, therefore, 330 meters per second. Okay, continuing on with measuring the speed of sound. Method 2, you can use echoes. So if you find a flat vertical surface, a wall or a cliff at least 50 meters away, one person smashes two pieces of wood together, and the other person basically sees that, starts his timer, and then the sound will come and he stops his timer. Okay? And then you measure the distance d between the clapping person and the flat surface, and the total distance will be 20 times 2d, because remember you've got 20 claps in this particular example. So the speed is the total distance divided by the time for 20 claps. Okay, so question with that. In an experiment to measure the speed of sound by the echo method, when a student stands 75 meters away from a wall, 20 claps are heard over a time of 8.77 seconds. Calculate the speed of sound. So again, pausing the video, seeing if we can get the correct answer. Okay, so the first thing you have to do is calculate the total distance traveled by the sound, which is going to be 20 times 2 times 75 meters, which will be 3,000 meters. Speed equals total distance of divided by the time for the 20 claps, so it's going to be 3,000 divided by 8.77. And then the speed of sound is going to be 342 meters per second. So here's some speed of sound examples. So the substance and temperature. So the speed of sound of air at 0 degrees, say, so in your fridge would be around 330 on I guess a winter's day in Malaysia. 342. Say in your freezer, it's going to be 325. Fresh water on a winter's day in Malaysia will be about 1,497. So you can see that the speed is a lot higher in water than it is in air. Seawater, which is slightly more dense, will be 1,560. Steel, which is a lot more denser, should be a larger number, and indeed it is. It's 5,000, and in a vacuum, it's going to be 0, because obviously you need a medium trick there. Okay. So Mach numbers. So a Mach number, probably you've heard it with jets, is the object speed divided by the speed of sound. Okay, so subsonic speed is less than 1. So normal jet aircraft that you fly around in usually. Transonic, Mach 1, and supersonic. So Mach 1 is probably the jet fighters flying over from Singapore when they're not on, when they're just going back to base. And Mach, supersonic Mach greater than Mach 1 is when they're actually in full formation. Okay, and hypersonic, as an example, would be like the space shuttle. So thunder and lightning. So this is quite common here. So it's a good way to measure how far the storm is away. Okay, so light reaches the observer in 60 millionth of a second, whereas the sound takes about 15 seconds. Therefore, if an observer 3 miles away sees a lightning flash about 15 seconds before hearing the thunder, every 5 seconds difference equates to around a mile. Okay, so you can kind of get an idea of how far the storm is going to be away from you. So a thunderclap is heard 12 seconds after a lightning flash. Calculate the distance to the lightning flash. Take the speed of sound as 340 meters per second. So if you pause the video now and give it a red hot go. Okay, so speed, of course, is distance over time. Rearrange the equation. Distance equals speed times time. So it'll be 340 times 12, 4,000 meters. So the distance is 4.08 kilometers is the answer. Okay, quite close. Okay, so another important tool used in physics is the oscilloscope, okay, which is a good way of measuring sound waves, especially. So the oscilloscope is a device with a microphone attached, so it can actually visualize a sound wave, and so what a screen looks like. It gives you the amplitude and also the wavelength. So the loudness of a sound increases with the amplitude of a sound wave. So that's a quiet wave there, and as it goes louder, the amplitude is going to be increasing. That's a loud signal. Pitch, of course, is about frequency, so the pitch of a musical note increases with the frequency. So a low pitch is there, that's a low frequency. A higher pitch, a higher frequency. So examples, a concert pitch A is 440 Hertz, a top C is 523 Hertz. So doubling the frequency increases the pitch by 1 octave, therefore an A above top C will have a frequency of 880 Hertz. And we also in music have quality and timbre. Okay, so the quality, also known as the timbre of a musical note, is what makes one musical instrument sound different over the other. Okay, so despite different instruments producing a note of the same loudness and pitch, the shape of the wave will be different. So there we go, that's a different kind of musical instruments create different kinds of waves depending on what they're made of. Okay, so the diagram opposite shows the appearance of a sound wave in an oscilloscope. Draw a second diagram showing the appearance of a sound wave of lower pitch but greater loudness. So again, pausing the video now and seeing what you come up with. Okay, so you should have seen that. Okay, so you've got an increase in okay, so if we make that the baseline, there's your increase in amplitude, but it's also of a lower frequency because the wavelengths, or the frequency has decreased. You can also measure frequency using an oscilloscope. So the time taken between peaks on an oscilloscope trace is equal to the time period capital T of a sound wave. There we go. Okay, time period between the wavelengths. So frequency, of course, we know is 1 over the time period. So therefore, if T, capital T is 0.05 seconds, then the frequency must be 1 over 0.05 or 20 Hertz. Okay, so here's a question here. The distance between the peaks of this oscilloscope trace is 4 centimeters. If the oscilloscope time scale is set to 1 millisecond per centimeter, calculate the frequency of the sound. So pause the video now and see what you come up with. Okay, so because 1 millisecond per centimeter means that the trace covers 1 centimeter every millisecond, time period will be 4 centimeters times 1 millisecond per centimeter, or 4 milliseconds. So 1 over capital T, 1 over 0.004, so frequency of 250 Hertz. Okay. So just like we always usually do to finish off, choose the appropriate words to fill the gaps below. So pause the video now and see if you can fill those answers in. Okay, so sound is a longitudinal wave that in air consists of a series of compressions and refractions. Sound travels fastest through a solid, but does not travel at all through a vacuum. A reflected wave is called an echo. Sound also undergoes refraction. On average, humans can hear sound frequencies from 20 to 20,000 hertz. So hopefully you got 100% out of those. Okay, so just to finish off, here is some interesting online simulations you could be interested in to kind of further explore sound, if that's your thing. Okay, and it'd be also great for revision.